In this video we are going to explain the different UPAC rules to identify and write names for hydrocarbons. The UPAC is the International Union of Pure and Applied Chemistry. It is an international scientific organization not affiliated with any government. The UPAC strives to advance chemistry in part by setting global standards for names, symbols, and units. Especially in this video we are going to tell you the different names for hydrocarbons such as alkanes, alkenes, alkynes, and aromatic compounds, and the difference between them. It will be important to familiarize yourself with these names because they will be the basis for naming many other organic molecules throughout your course of study. Hydrocarbons are the simplest organic compounds, containing only carbon and hydrogen. They can be string chains, branched chains, or cyclic molecules. There are three types of homologous families of hydrocarbons: alkanes, alkenes, and alkynes. Alkanes contain only single bonds between carbon atoms. Alkenes contain at least one double bond. Alkynes contain at least one triple bond. Most of these types of hydrocarbons can exist with the same chemical formula in different form of chemical structure. When a compound has the same chemical formula but two possible structures, these two structures are called isomers. Also exist aromatic compounds. They derive their names from the fact that many of these compounds in the early days of discovery were grouped because they were oils with fragrant odors and scents named aromatic.
Alkanes use the suffix "ane", and depending on the number of carbons, they use the Greek prefix meth, eth, prop in case of 4 carbons, but in case of 5, pent, ex, apt, oct, non, and in case of 10 atoms, apt. I'll show you one example, which is pentane. Its chemical formula is C5H12. In here, you can notice that pentane has 5 carbon atoms, and that's why its name has the prefix pent. And as it is an alkane, it has the suffix "ane". Some other examples are methane, propane, and decane. In a condensed structural formula, each carbon atom and its attached hydrogen atoms are written as a group. Also, we can represent this as an expanded structural formula, drawing each carbon and each hydrogen atom. Here is an example. The example is pentane, which chemical formula is C5H12. This is the expanded structural formula. In here we have the 5 carbon atoms and surround them the 12 hydrogen atoms. Of course, here we have the condensed structural formula, which is CH3, CH2, 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 and CH3 again. Here I have 2 more examples. In here I have propane and ethane, and these are the expanded structural formulas. I will write the condensed one, which for ethane is CH2, and for propane it's CH3.
First of all, we have to know what is an alkane. An alkane is a hydrocarbon that contains carbon-carbon double bond. This type of hydrocarbons have a general formula, that is, number of carbons is equal to 2 times the number of hydrogens. 3 examples are presented in the following image. First, ethane that has 2 carbons and 4 hydrogens. Then, propane that has 3 carbons and 6 hydrogens. And butane that has 4 carbons and 8 hydrogens.
Well, we're gonna learn how to write the equation from the name. First,
we're gonna write the main chain, that is pentene. And this is made of 5 carbons. And then we're gonna put the double bond between the third and the second carbon over here. Then we're gonna write in the third carbon we're gonna write the methyl group, as it says in the name, that is CH3. Then we're gonna add up the hydrogens until every carbon has their bonds complete. Here is H3. And this can also be write as CH3, CH, CH2, CH3, and here. First, this is the first example. This is the easiest one because it doesn't have ramification. Then we're gonna use the UPAC rules to name this alkane because it has double bond. This is because the number of carbons is propane. We have to identify which of these is the main chain. We have this and this. I'm gonna use this because it's easier. And well, the main when it's an alkane, it has to be the chain with the double bond. Well, first we have to name the longest chain that have 5 carbons. So it is pentene. Then we have to put numbers on the chain, on the longest chains, and then we have to put the number the nearest number to the one that when it finished the double bond, so it's 2. Then we have to put the names of the ramification. This is a methyl group, and it's in the 4 carbon in this chain, so it's gonna be 4 methyl 2 propane, pentane. First, in this example, we're gonna try a difficult one. First, we have identified the longest chain with the double bond, which is this one. I'm gonna put the numbers on the carbons. 1, 2, 3, and 4. There are 4, and it's an alkane because it has a double bond. Then, because it's 4, it's butene. Then, as we know in alkanes, we have to put the nearest number to one that is involved in the double bond, and in this case is 1. Then we're gonna identify where the ramifications and which type of ramification is. This is a methyl, and these other two is methyl again because they are equal. Then you're gonna put a number of carbon in which they are located, which are 1 in the soup and the other 2 in the third. And because they are 3 is 3 methyl. And the number of this hydrocarbon is 2, 3, 3, 3 methyl, 1 butene.
The alkynes are the third homologous series of organic compounds of hydrogen and carbon, where there is at least 1 triple bond between the atoms in the molecules. The next 7 rules are for naming alkynes. The first one says that the yn is suffix, the ending, indicates an alkyne or a cycloalkyne. 2. The longest chain chosen for the root name must include both carbon atoms of the triple bond. 3. The root chain must be numbered from the end nearest a triple bond carbon atom. If the triple bond is in the center of the chain, the nearest substituent rule is used to determine the end where numbering starts. 4. The smaller of the two numbers designing the carbon atoms of the triple bond is used as the triple bond locator. 5. If several multiple bonds are present, each must be assigned a locator number. Double bonds precede triple bonds in the UPAC name, but the chain is numbered from the end nearest a multiple bond, regardless of its nature. 6. Because the triple bond is linear, it can only be accommodated in rings larger than 10 carbons. In simple cycle alkynes, the triple bond carbons are assigned ring locations 1 and 2. Which of the two is 1 may be determined by the nearest substituent rule. And 7. Substituent group containing triple bonds are ethynyl group and propyl group. We're going to name this alkyne, so first we start numbering the carbons. And since the triple bond is in the middle, it doesn't matter in which way we do it. Then there are 4 carbons, so it will be a bot. And we have a triple bond, so it will be an alkyne. And finally, the triple bond is in the second carbon, so it will be a 2, since the 2 is our triple bond locator. And finally, we'll have a 2-butyne. We're going to do the same thing in the next 2 examples. First, we look for the number of carbons. Then we look for the triple bond. And finally, we look where it starts, and that will be our triple bond locator. In this example, we see that there is another chain. So the first thing in this case we're going to do is to select the longest chain. Now we are going to draw the 1-butyne. So it's a bot, so it will have 4 carbons. Then we know that it finished with Y and E, so it will have a triple bond, and the indicator says that in the first carbon. So this is how it looks right now. Then we need to put the hydrogens, and in the first carbon we have 3 bonds, so it will have one hydrogen, and the other ones we fill it like this. And then we finish. And it will look like this. There is a carbon, another carbon, and the triple bond is there. So it will be a 1-butyne.
Aromatic is a hydrocarbon with alternating double and single bonds between carbon atoms forming rings. The configuration of 6 carbon atoms in aromatic compound is known as a Bunsen ring, after the simplest possible such hydrocarbon, benzene. To name aromatics based on the UPAC system, some common substituents like NO2, Br, and Cl can be named this way when it is attached to a phenyl group. Long chain carbons attached can also be named this way. The general formula for this kind of naming is positions of substituents, if they are bigger than 1, plus the number, plus the substituent, n, plus benzene.
For example, chlorine Cl attached to a phenyl group would be named chlorobenzene, chloro plus benzene. Since there is only one substituent on the Bunsen ring, we do not have to indicate its position on the Bunsen ring, as it can freely rotate around and you would end up getting the same compound. Nitrogen dioxide, NO2, attached to a phenyl group would be named nitrobenzene, nitro plus benzene. Since there is only one substituent on the Bunsen ring, we do not have to indicate its position on the Bunsen ring. A more complicated simple benzene naming example. 2 chlorines attached to a phenyl group will be named 1,3-dechlorobenzene, 2-chloro plus benzene. Note that standard nomenclature priority rules are applied here. causing the numbering of carbons to switch.
Structural formulas for aromatics show all the bonds in the molecules as individual lines. You need to remember that each line represents a pair of shared electrons. Notice that the way aromatics is drawn bears no resemblance to the actual shape of the molecule. Aromatics are not flat with 120-degree bond angles. This mismatch between what you draw and what the molecule actually looks can lead to problems if you are not careful.
For example, chlorine and 3-ethyl attached to a penyl group would be named 1-chloro-3-ethylbenzene, chloro plus benzene plus ethyl. TNT, as named under the IUPAC nomenclature. Note that since the IUPAC nomenclature does not recognize toluene as the primary base of this compound, substituent priorities are reverted to normal defaults. As a result, TNT in IUPAC is named 2-methyl-1,3,5-trinitrobenzene. 2,4-dibromophenol, as shown in this diagram, is valid in both the common nomenclature as well as the IUPAC nomenclature. Phenol, benzoic acid, and benzaldehyde substituents are allowed to be used in the IUPAC naming conventions, and the base naming priority rules are applied in the nomenclature process.
Organic chemists classify chemical compounds according to their functional group. A functional group is a special arrangement of atoms that is mainly responsible for the chemical behavior of the molecule. Functional groups also determine some of the physical properties of the molecule. When one or more functional groups are attached to a hydrocarbon, the resulting compound is referred to as a hydrocarbon derivative. Hydrocarbon derivatives are compounds made up of carbon atoms and at least one other atom that is not hydrogen.
In organic chemistry, functional groups are specific groups of atoms or bonds with molecules that are responsible for the characteristic chemical reactions of those molecules. The same functional group will undergo the same or similar chemical reactions regardless of the size of the molecule it is a part of. However, its relative reactivity can be modified by nearby functional groups. The following is a list of common functional groups. In the formulas, the symbols R and R' usually denote an attached hydrogen or an hydrocarbon side chain of any length, but may sometimes refer to any group of atoms.